Balloon 411 Weather Theory and Reports. Let's chat about weather and why it's such a big deal for balloon pilots. You see, weather isn't just about checking if it's sunny or rainy. It's a whole intricate system involving atmospheric pressure, air temperature, wind, clouds, and precipitation. Balloon pilots need to get the lowdown on all of these to ensure safe and successful flights. Now, the FAA has some advisory circulars like ORODO 6A and ZODO 45E that are like weather Bibles for pilots. There are also plenty of other texts and online resources that are like treasure troves for learning about weather. NOAA even has this cool weather tutorial that's super handy. The atmosphere, that big blanket of air hugging our Earth, is where all the action happens. It's got layers, and the troposphere is where the real party is at. That's where weather events like storms and clouds go down. Oh, and there's this boundary called the tropopause at the top, which messes with moisture and sometimes leads to turbulence. Now, to keep things standardized, we've got the International Standard Atmosphere, ISA. It sets the baseline at 59 degrees F or 15 degrees Celsius and 29.92 inches of mercury, Hg, or 1013.2 millibars, MB. You know, just so when pilots talk about weather, they're all on the same page. The pressure drops as you go up, roughly 1 Hg per 1,000 feet for the first 10,000 feet. And there's a standard temperature drop too, about 3.5 degrees Fahrenheit or 2 degrees Celsius per 1,000 feet up to 36,000 feet. At sea level, the atmosphere is pushing down with a force of 14.7 pounds per square inch. It's like having a 14.7-pound weight on every inch of the Earth's surface. That's a lot of pressure. Balloon pilots need to wrap their heads around all this to make smart decisions and keep their flights smooth and safe. Imagine yourself standing at sea level, and you can feel the pressure of the atmosphere surrounding you. It's like a force pressing on your skin from every direction. Now, this atmospheric pressure isn't constant. It changes with factors like altitude, temperature, and air density. And guess what? These changes have a significant impact on how balloons perform. They influence crucial aspects such as useful load and burner performance. When we talk about measuring atmospheric pressure, we often use millibars, MB. But here's the twist. Since weather stations are scattered globally, we need a standard reference. So each station adjusts its barometric pressure readings to sea level pressure, adding approximately 1 HAG for every 1,000 feet of elevation. This standardization is crucial to ensure pilots set their altimeters correctly based on current pressure readings. Now let's shift our focus to temperature. It's essentially a measure of how much heat is present, and we gauge it using a thermometer. During the day, the Earth receives heat from the sun, a process known as insolation. When night falls, the cooling occurs, and that's termed terrestrial radiation. In the temperature world, we encounter two scales, Fahrenheit, F, and Celsius, C. For Fahrenheit, freezing happens at 32 degrees D and boiling at 212 degrees. On the Celsius scale, freezing is at 0 degree and boiling at 100 degree. In recent times, the U.S. has been adopting Celsius more in weather reports, aligning with international agreements, especially those from the International Civil Aviation Organization, ICAO. Temperature variations are where things get intriguing. Diurnal variation, or the change in temperature from day to night due to the Earth's daily rotation, is a constant player. Water and terrain also become protagonists in this weather narrative. Water doesn't experience temperature changes as intensely as land does. Prevailing winds and altitude add their own twists to the tale. Normally, temperature decreases as you ascend in the atmosphere. However, sometimes it behaves contrarily, increasing with altitude. We call this an inversion. Inversions can mess with the expected temperature drop with altitude, especially near the ground on clear nights. So there you have it, a detailed exploration of atmospheric pressure and temperature. Understanding these factors is like holding the key to unlocking the secrets of a safe balloon navigation. Let's talk about how our planet gets its warmth. The sun. The sun sends its energy through space and the Earth's atmosphere, heating up the Earth's surface. Now, once that energy gets here, it transforms into heat in three nifty ways: radiation, conduction, and convection. First up, we have radiation. Think of it as heat traveling through electromagnetic waves. The cool part is, no material is needed between the heat source, like the sun, and what's soaking it in, that's us or the Earth. It's like the Earth's surface, water vapor, and particles in the atmosphere catching these heat waves. Next, we've got conduction. It's all about the transfer of heat between substances or within a substance. Just like some materials conduct electricity better than others, they also conduct heat differently. Air isn't the best at this game. It's a pretty poor conductor compared to something like silver. Silver can pass a whopping 20,000 times more heat than an equal mass of air across the same temperature difference in a given time. Conduction matters most at the Earth's surface, where the atmosphere meets the ground or water. Let's discuss more about convection, the transfer of heat in a fluid, like when you see your soup bubbling in the kitchen. In the atmosphere, this happens when the sun warms up the ground. The warm ground heats the air right above it through radiation and conduction, making that warm air rise. Meanwhile, the cooler, denser air from up high scoots in to replace the warm air near the ground. Convection can go either up or sideways, and when we're talking about horizontal movement, we call it advection. This horizontal heat travel by wind is a big deal in meteorology. In fact, the amount of heat moved horizontally over the Earth's surface by advection is about 1,000 times more than what's moved vertically by convection in the atmosphere. Let's explore the details of atmospheric processes, beginning with the adiabatic process, a term for how air changes temperature without swapping heat with its surroundings. Picture this. When air rises, it expands into a larger volume, cooling down. Conversely, when it descends, it gets compressed, heating up. It's a natural interplay of warming and cooling as air moves up and down. Air masses are like the actors in our weather narrative. These are massive bodies of air with uniform temperature and humidity characteristics. They're big. We're talking over 700 kilometers wide, and their behavior is influenced by their source region, like polar areas or tropical oceans. As air masses travel over land or water, the local terrain tweaks their properties, affecting stability, cloud types, visibility, precipitation, and more. Now let's chat about pressure systems, the big players in the atmospheric game. Low-pressure systems or cyclones have decreasing pressure towards their center, and winds swirl counterclockwise in the northern hemisphere. They're not the friendliest for flying, with low clouds, restricted visibility, gusty winds, and turbulence. On the flip side, highs, or anticyclones, have increasing pressure towards their center, and winds swirl clockwise in the northern hemisphere. These are more pilot-friendly, offering clear skies, light winds, and less turbulence. You'll often see a cycle of highs and lows cruising through the temperate zones from west to east in the northern hemisphere. In winter, things speed up as low-pressure systems intensify, and highs stretch southward. Troughs, long stretches of low pressure, bring turbulent weather, while ridges, long stretches of high pressure, are generally good for flying. Think of it as a grand atmospheric ballet. Highs and lows waltzing across the skies, air masses playing their parts, and the stage set by the diverse terrains they pass over.